Today we're going to do section 3.3, at least part of it, differentiation rules. Now the rules are excellent because they really cut down on the time so that you don't have to mess with the limit every single time. Okay? We really cut to the chase and get to it a lot faster. So first rule, the easiest one, is that the derivative of any constant is 0. Now that's remember the derivative means slope, and the constant is a function when y equals to some number, constant number, that means your line is flat. Therefore, the slope is 0. So it's not surprising the derivative of a constant is 0. We already know that from previous experience. However, we're going to prove it here formally. And the constant rule, the proof is also very simple, but we're going to do it anyway, just for the principle of it. And so the rule says this: the derivative of a constant, d by dx, of some constant, c, is 0. Doesn't matter what the constant is. Derivative of a constant is 0. And remember, this means the derivative is one of the ways to say it. And therefore, now what is the proof? The proof is this. Let's say you have a function, okay, f of x, that equals to some constant. Then the derivative, by definition, is f prime of x. And you say, why are we not using that right now? Why are we saying f prime? No reason. It's just habit. Your book use it, so I do too. And so f prime of x equals the limit definition, which is the limit as h approach 0 of f of x plus h minus f of x. This is just the definition, okay? I'm just repeating the definition here, and I haven't done anything. Is when you prove a math theorem or some problem, is good to first write down where you're starting from. Like, what is your foundation? Where are we going from? You got to figure out where you're starting from first, so that you're building from there. So we're building from the basic. This is the definition of the derivative, and then what is and what's f(x) plus h? Well, f of anything is c, so f(x) plus h is also c. So that equals the limit of c, okay? That's f plus h. And then f of x is also c, because it's a constant. And whatever you input, the output is always c. So divide by h as h approaches 0, and that is equal to 0. Because, as always, h isn't actually 0. We're just approaching it. So therefore, it's 0. And by that, I prove that if f of x is a constant, regardless of what constant it is, f prime of x is automatically 0. Okay, so that's good. Next, the power rule. But before we do the power rule, I guess we will do example 3.18, which is we're going to take the derivative of x cubed. That is, we're going to find this thing. This is example 3.18, which is on the next page, 248. So, page 248, example 3.18. We're going to take the derivative of d of dx of x cubed. So notice that we want to go back to using this formula. So you might ask, but when do I use this notation and when do I use that? That's not something, let's not worry about that, okay? You just use it when you feel like it. What if you don't know what you feel like? Then I don't know, do something. You'll get it soon enough. It's a habit. Everybody does it. See? So eventually, as you work more, you will gain the habit and get into the groove like everybody else. So, but for now, we need to figure out the derivative of x to the power 3. And what are we going to do with it? So by definition, we're going to follow this definition right here. We have already written it down. And then plug this x to the power 3 as f. Okay, f. And follow this definition, we get the limit as h approaches 0 of f of x plus h, which in this case is x plus h to the power 3. Then subtracted f of x, which in this case is x to the power 3. Okay. And then divided by h. Alright, so far so good. Now at this point, you're gonna multiply this thing out. Now this was done at some point in algebra, right? Remember how to do this? This thing is done in a special way. That is, you draw a triangle. I will draw the triangle right, maybe here. Okay, here's your triangle. First you have 1 and 1, okay? And then it becomes 1, 2, and 1. What happens is you add 1 plus 1, it becomes the 2, where your outside units are always 1. And then the next level, it becomes 1, 3, 3, 1. Again, you're adding these two numbers. 1 plus 2 is 3, and 2 plus 1 is 3. So you're doing this addition thing. Whereas the outside numbers are always 1 coming out. And the fourth, this is the third level. The fourth level is 1. This is 4, because 1 plus 3 is 4. 3 plus 3 is 6. 1, 4, 6, 4, 1. And this triangle goes on. Okay, the 4 comes from 1 plus 3, and 6 comes from 3 plus 3, and the 4 comes from 3 plus 1. Now this triangle goes on indefinitely, and that is how you're going to multiply this thing. Okay, that's the trick. And to expand this thing, the rule says that you will go following this. We're on the third level, the third power. So the third level is 1, 3, 3, 1. Therefore, the expansion of x plus h to the power 3 equals to x to the power 3 plus the second number is 3 x 2h. This power goes down by 1, and h goes up by 1. Plus the next number is also 3 3x h squared. Notice x is going down 1 at a time, whereas h is going up 1 at a time in terms of power. And then plus h to the power 3. And that is the expansion of x plus h cubed, if you remember, or if you sit down here and multiply it out by hand, which we're not going to do because we already know this. Okay, this is the trick that you use. And what is this thing? This is also called the NCR, I believe. NCR. And we'll go into that a little bit more later. Okay, it's a bunch of numbers that you added this way from statistics, where you, by the time if you do this the brute force way, the hard way, then you will find out that it fits this rule. And the rule comes from doing this the hard way. Let's see, how's my, yeah. So we got this thing out, okay, the easy way by following this rule, and then we minus x cubed, and then divide it by h, where h is going to 0. And that's so far we're doing the derivative. So then now we do a bit of algebra grunt work. So that equals to x cubed got subtracted out. So you have this stuff, which each one has an h in it. Therefore, maybe I should talk on this side. Okay, so each one has an h in it. Therefore, we will factor out the h. So what do we get? Remember, x3 got subtracted out. So we have, we'll factor out 1h. And then we have 3x squared plus 3x plus h, right? We factored out 1h plus h squared, and then divided by h. Divided by h as h approaches 0. And h is not 0 yet. We're just in the delta neighborhood. So we can cancel this out. Cancel. And then let h goes to 0. If after you cancel it, as h goes to 0, these terms disappear, become 0. So the only thing you have is 3x squared. And that is the derivative of x cubed. All right, so far so good. And speaking of the delta neighborhood, I forgot to mention earlier that the derivative is also denoted as the triangle y over triangle x. as the limit, okay? The limit as triangle x goes to 0. I think that's one of the many definitions. And I told you that the triangle is pronounced delta. I forgot to mention that this is also delta. This is from the delta epsilon definition. So the reason there are two deltas, this is the capital delta in Greek, and that's the small letter. I forgot to mention that, so I figure I should mention it. And that's why they're both called delta. And why do we like Greek letters? Well, we do. Okay, it's a mathematical tradition. So remember that the big triangle is the capital delta, and that's the small delta. Yeah, but we're not going to use that much actually. But if you ever see it, you know what it is, and not be, confused. Like, what's that? is another way of saying derivative. There are many ways to say the derivative. All right. So now with this particular experience, now we're gonna show the power rule, which is a very easy theorem to apply, but is quite lengthy to prove. And not lengthy, more like tedious in the terms that we have a lot of stuff to have to write down. So let me clean the board. Now, remember that this triangle I have drawn here a little earlier is called the NCR. It is in your calculator, if you have any kind of scientific calculator, and is from statistics and is called the combination. Okay, there's another thing called permutation, and that's different. This is just the combination. You can calculate the combination by building this easy triangle, or you can use your calculator and punch it out. And apparently, the NCR is also expressed this way, in parentheses, the n on top and r on the bottom. All right, this is a notation. It represents this particular triangle, the numbers going, well, the way it is. And anyway, with that, we need to prove the power rule, which is, so far we have done x to the power 3, but now we want to discover a rule for x to any kind of power. That is, if f of x equals to x to the power n. So here's our problem, our theorem, which is on page 249. And what we're trying to prove is called, where did it go? Okay, we're trying to find the derivative of f of x, where f of x equal to x to the power n being any integer. In this case, any positive integer for now. What is the derivative? The derivative is, and you will memorize this, and this will become part of your being as you learn calculus, is if f of x equal to x to the power n, then f prime of x, the derivative, is nx n minus 1. You take the n and put it in front, and then you reduce n by 1, which is what worked out in the previous example. In the previous example, we did f of x equal to x to the power 3. So the derivative, as we calculated, was 3x squared. But right now, we're going to calculate for anything. N equals to whatever number anybody can imagine. This rule will still work. Okay, so it applies to all n, not just n equal to 3. And having said that, let's crank it out. So let's look at the proof. In this case, the proof is here. Here's our proof. F prime of x. To prove it, we'll go back to the good old definition of f prime, the limit definition, where a equals a limit h approach 0, where f of x, in this case is x to the power n, you need to do f of x plus h, which is x plus h to the power n, minus f of x, which is just x to the power n, and the whole thing will divide by h. The previous example we did, which is just where n is 3, gives you a feel of how this proof is going to go, right? And the principle is the same. Now, the most complicated part of this proof is we need to expand this thing to the power n. The expansion of to the power n follows the rules of combination. Before we followed the rule for 3, where n equals to 3, but now we're going to follow the rule for n in general, which says, okay, x plus h, the expansion of x plus h is. So this equals the limit as h goes to 0. I'm starting to write from that end because this is going to take quite a bit of space. All right. We'll draw a big, long division line. And this thing, you following the combination rules right here is, and this was taught in earlier algebra class, like college algebra sometimes. But if you don't remember it, it's of no real consequence. It's just a formula, a convenient formula for expanding x plus h. So the formula says this: you start with x to the power n, and then plus, and then nx n minus 1, and then plus NC2 is what that is. Okay, you calculate this value by punching in your calculator if necessary, or building a little triangle if n isn't too big, and where x plus x n to the n minus 2, and then h will increase the squared. Well, where's the h here? Yeah, there needs to be an h. The point is, the n function, the n will go down one at a time, and h will go up one at a time until it gets to dot dot dot, until h goes to the power n. It's very similar to what we did before when n is equal to 3, but the principle is the same. So n goes down, and your coefficients following the NCR principle, and then you finally get there. And then minus x to the power n, okay, the whole thing divided by h. All right, so as before, when you do this, what you get, flip to the next page, is you get something like your x power n will subtract out at the end, okay? Because there's an x to the power n in this thing, and then you will subtract it, so you got rid of it. And the rest of the stuff all has at least one h in it, which very conveniently will cancel out, just like the previous example. So that's what we're going to do. That will be equal to, we're still doing the limit as h goes to 0. Okay, we'll factor out 1h out of this pile of stuff. You factor out 1h, so you have nx n minus 1. Now notice this is exactly our answer, and that matters because plus some combination of you will have 1h left. Okay, all the h's get knocked down by 1 from your factoring. So you will have 1 less h in all the rest of the stuff. So the next one will be a pile of stuff with h, just h. And the next one will be a pile of stuff with h squared all the way to h n minus 1, because everything lost 1h. Okay, and then well, the stuff in here, you just copy those things down, and I'm going to skip it because we don't really care what they are. All we care about is the fact that they have an h attached to each one, and we are allowing h to go to 0. So as h goes to 0, oops, sorry, that's just h. So here's h. So we cancel out this h first. H is not 0. It only gets there as is in the delta neighborhood as 0. So you're allowed to cancel it. Once you cancel it, these things all disappear. Okay, there's h. H is going to 0. So that's all gone. And we only have the answer being what we were looking for, nx n minus 1. So that is a fairly tedious proof for something that comes out to be nice and neat and clean. So that's how you take the derivative of anything that looks like x to the power of a number. All right. So when you see this part, sometimes people get intimidated because they see a lot of symbols, and then especially if they forgot what this thing is, then they're like, what is that? I don't understand it. It's too hard. Well, it's not. It's the NCR, and there's a certain formula to calculate the numbers of how you multiply this thing out. That's all. In other words, it's kind of an account, keeping counting. Okay, the combination is just counting. Well, statistics is all about counting, really. I don't really, go into statistics that much because it's too much counting, a lot of grunt work. But a lot of mathematicians are not as lazy as me, and they are very much into statistics. But we can totally use it here, being that we are just stick it there and then it's all disappeared anyway, so we don't really have to work very hard. I like theoretical mathematics because it's not near as much grunt work. And as an example, let's look at example 3.19. This is on page, well, whatever, right after this. And then we have, say you want to find the derivative of f of x equals to x to the power 10. Which, if you were to use the original limit definition, that would have knocked you out. It's so much. You have to multiply this thing by itself 10 times. Imagine doing that. I'm not doing it. I've never done it and never will. But instead, you simply follow this formula. What is the f prime of x? The formula says you take the 10, the number on top, put it on the side, and then reduce it by 1. So f prime of x is 10x to the power 9. Done. See? It cuts out so much work.